Okay, let's get started. So, in the previous class, we learned about bits. So, bits is the billion of instructions per second. So, actually, so you can think that the bits is the very intuitive performance metric because bits just counts the number of executed instructions per unit time, right? And then we can say that if our computer system can run more instructions, then we can say that, oh, our computer system is fast, which means performance is higher. Okay? But you need to remember that in order to use MIPS as a performance metric, then its condition should be met. So you can find the relative question in form of form of assignment number one. So in the homework assignment number one, I asked about the MIPS and then how I asked how we can use MIPS for the performance method. Okay. So sometimes students are confused because actually this as I said, the MIPS is the very intuitive performance metric. But in order to use the MIPS, we need to actually these conditions should be met. So we need to remember. So and then in the previous class we learned about the power consumption of a processor or a computer system. So usually the processor is the main part of this. I mean the CPU is the central processing unit. CPU is a main component of our computer system, right? So which means that if we will talk about the power consumption of our computer system, and we just focus on the power consumption of the CPU traditionally, and traditionally. But recently, our computer systems have many other components, such as, for example, GPUs. So actually, we use GPUs for the graphics application, but nowadays we use GPUs for some parallel processing applications, such as AI applications or neural network applications, right? So that's why GPUs are very popular recently, because of the price is very high and expensive. So the GPUs also consume much power, but usually we just talk about the power consumption of a computer system, and we focus on the power consumption of a CPU. Okay, and then the CPU is the kind of digital system, and then we make digital systems using semiconductor technologies, right? So actually, all electric devices, and then all digital systems, and then actually all chips, all integrated circuits consume electric power, right? It's obvious, right? Because we need to provide the electric power to the circuit to run integrated circuits, right? So and then when the voltage is provided, and then current flows to circuit, and then if there is voltage that is actually the gap of the electric potential level, and then current flows from high voltage to the low voltage, then the circuit consumes electric power. So we can write the power consumption equation like this. Then actually its power consumption equation is explained about the dynamic power. Okay, so actually CPU the CPU, we can split the power consumption to the where is it? Okay, dynamic power and static power. Okay, so dynamic power is that a circuit consumes electric power when the circuit's behavior is circuit state is changing. So which means that actually I said that our CPUs are kind of this the system. So actually CPU generates the output 0 or 1. And then this output is changed by input signals like also 0 and 1. And the input signals are changed and electric powers are also consumed. But also, when the output signals of a circuit are changed from zeros to ones or ones to zeros, then this circuit consumes electric power, right? So, and then this power consumption is called dynamic power. Then static is the opposite meaning of the dynamic power, right? That means it's not dynamic. So which means even though the circuit does not work, but the electric power is consumed. And then I said, in this graph, I said that it is because our circuit is not a perfect device. Our circuit is not perfect. So actually, theoretically, we can assume that our circuit, actually we use the CMOS circuit. And then if the CMOS circuit does not work, then this CMOS circuit does not consume electric power, theoretically. But even though the circuit does not work, current flows from high voltage VDD to ground. Even though the circuit is turned off. I mean, the turned off means that the output is not changing. Okay. The circuit's output is not changing. However, the current flows and then the electric power is consumed. So traditionally, the static power occupies the very little portion of the total power consumption. But recently, the transistor size is very small. So which means that actually the transistor cannot block the current flow perfectly. So actually, even though this CMOS circuit does not work, the current flows, so actually very high current. The current flows, then static power is consumed. And then recently, the modern CPU consume 50% of total power as static power. Okay, it's amazing actually. So we also applied some techniques to reduce the static power. So actually, and then I also explained that we used multi-core architectures to improve the performance. Actually, when we learned about the performance of the CPU, so you need to remember the equation how to measure the performance of a single core CPU. What is it? So I mean the response time. T execution equal CPI. Yeah, CPI is also included in CPI, but the first number of instruction count. I see and clock cycle, right? Good. Is C. Then actually the clock cycle is the 1 over frequency. So the easiest way to improve the performance is to increase the clock frequency, right? Because F is here. And then we can easily, I said that we can easily increase the clock frequency if we use the ferro semiconductor technology. Okay. But if we use actually, let us assume that we use the same semiconductor technology. And then on this condition, I want to increase the performance, which means that I want increase the clock frequency of CPU. And then usually this is called overclock. Overclocking. Okay. So if you are interested in desktop computer system, then I believe you have heard about the overclocking, right? So and then if with the overclocking, we can increase the clock frequency, right? And then in order to apply overclocking to our computer system, then we need to actually increase supply voltage, right? So if we are interested in overclocking, and then in order to apply overclocking for our CPU, then we need to increase the supply voltage, right? It's also same to other digital devices such as the main memory like DRAM. Also, actually, we increase the clock frequency of the main memory or CPU for overclocking. Okay, so which means that we need to in order to increase the performance, then we need to increase the supply voltage, and then we learned about the equation of the dynamic power consumption, right? What is the P dynamic for alpha is the activity factor, then C the capacitive load, then B squared and F. Okay, if you see these equations, then we can know that dynamic power is proportional to the clock frequency. But I said, if we use the same semiconductor technology, then in order to increase the clock frequency, which we need to increase voltage also, supply voltage. So actually, we also need to increase the supply voltage to B squared. And then actually, the F is proportional to supply voltage. So this means actually P dynamic is proportional to F Q. Okay. So that's the problem. If we want to increase the performance of a CPU twice by double, then the power this CPU will consume 8 times of power, because the dynamic power is proportional to the frequency, the cube of the frequency. Okay. So it will consume much power. So as I explained, increasing the clock frequency is the easiest way to increase the performance, I mean the latency. So actually increasing the latency is very require higher power consumption. So, but we can increase the other performance measure, like the throughput, right? So for example, if we use the dual core, so which means that there are 2 cores in a single CPU chip. So and then I explained that a core is the independent processor that can execute independent thread. Okay. So there are 2 cores, and then with the 2 cores, the theoretical throughput is double. Okay, because there are 2 cores. So think like this. If we increase the frequency, and then if we increase the frequency twice, then power is increased by 8 times. But if we just add 1 more core, then throughput is increased by 2, then power consumption is actually increased by twice, double. It's the power consumption is just double. It's proportional. It is because P equal alpha C E square F. And then if we increase the number of cores, which means that only C is increased because the area is increased, right? I mean the capacitance growth is proportional to the area of a CPU, right? And then if we add one more core, then area is double. Okay, that's why the performance power becomes twice of the original power. Okay, that's why we use the multi-core architecture. So benefit of a multi-core architecture means that we can increase the throughput, okay, and then also we can concurrently execute many threads with the multi-core architecture. So usually server CPUs have many cores, like Intel Xeon CPUs have the high performance Intel Xeon include 40 cores, okay, in a single CPU chip. So the server needs to run many threads from many users, okay, but in order to use the multiprocessor, then actually we cannot increase the performance of single thread application, right? So think like this. Okay, this is the task. Then we cannot divide this task into two. And then we invest two people, two workers. Then, but if this task is not divided, then we cannot reduce the execution time for this task. That's the problem of multi-core architecture. Actually, the performance of a single thread cannot be improved with the multi-core architecture. So there are many issues like the communication issues or synchronization issues. Okay? But in this course, we focus on the single core architecture. Okay, and then if you take the advanced computer architecture course, then you can learn about the multi-core architecture. Okay, so in this class, today's class, I will discuss about the benchmark of definitions and Moore's law. It's very important law in the CPU industry. So okay, I will explain. So in chapter 1, we learned how to measure the performance of a computer CPU, right? And then we can measure the performance of a CPU by comparing the performance of a certain CPU with the performance of another CPU. It's a baseline CPU. So if you read the homework assignments, then you can find that in the instruction of the homework assignment, you can find that so we can measure the power like the PA divided by PB, and then if this is the 1.NN, then we can say that the performance of PA is higher than NN% compared to the performance B, performance of B, right? So if you read the homework assignment instruction, then you can find this sentence. So actually, we can measure the absolute execution time of application on a certain computer system. But by doing this, we cannot get any information. But so for example, so I run application A on my smartphone, Galaxy smartphone, and then it takes 10 seconds. Oh, can you say, oh, my Galaxy smartphone is good smartphone? Well, that smartphone, if we just consider the performance. Can you say the performance of our smartphone? No. You cannot say. So just 10 seconds. So if what we can know is that, oh, if we just run application A, then it takes 10 seconds, and that's it. So actually, we can know the performance of our computer system by comparing the performance of the baseline system, so or other computer system. That's why I also add instruction on the homework problems. And then how can we measure the performance? So actually, the CPU is the general purpose processor, so which means that we can run any application using CPUs. But problem is that there are many types of applications that can be executed by CPUs. So for example, there are CPU A and CPU B, and then we can measure the performance using application A on CPU A. And then let us this is the Samsung, and then this is Apple. Let us, and then Apple runs the another application B on their CPU B, okay, Apple A chip. So, and then they want to compare they want to advertise that, oh, our CPU is better than their CPU. But what's the problem? Applications are different. So actually, in order to compare the performance of hardware CPUs, then we need to run the same application, which means the same software. Because I said this equation is very important. So execution time, instruction count, CPI, and P. Actually, the instruction count and then the part of CPI is determined by software. And then we know that if the software is changing, the performance can be also changing. But in order to compare the hardware fairly, then the software should be the same. Okay, that's why we need benchmark application. So benchmark applications are the bundle of software that is used for measuring the performance of many computer systems. So these are the standardized applications which are used for measuring the performance. And this type of applications are called the benchmarks. Okay. And then we use benchmark application for measuring the performance. And then if we use the same applications, then the software part is the same, and we can fairly compare the performance of the hardware. Okay, that's why we use a benchmark. Right?
그러면 소프트웨어 A로 쓸 때 더 좋은 시스템이 다른 소프트웨어로 쓸 때 더 안 좋아질 수도 있어요.
Yeah, 그렇습니다. Yeah. So here that if we use the different software for measuring the performance, then the performance can be changing, and that's true, right? Because performance is also determined by software, and also, you know, so things like this. So Intel i7, there are Intel i7 CPU, and then AMD Ryzen 7. And we want to compare the performance of these two CPUs, okay? And then we run the same application A. Then the performance can be better with the i7, but the performance can be lower. And if we use the different application, like the application B, then performance can be better for Ryzen 7. Because CPU vendors can use different type of hardware processors. And then if some architecture or some processor can be better for some specific applications, okay? It can happen. So actually, the benchmark we use many applications as benchmark application, right? So if we just use the one application A, then CPU vendors will only focus on this one application. But it's ridiculous, right? We can run any type of application using our CPU, but if we use the one benchmark application, then CPUs will increase the performance for only these applications. And then if we run the other applications such as the application B, C, D, blah, 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 then the performance can be lower using the other applications. So we need to avoid this situation. So actually, the most famous benchmark for measuring the performance of a CPU is the spec CPU benchmark. And then spec CPU benchmark suite includes many applications. So many popular applications. The popular means that we use these type of applications frequently. So you can actually there are many types of spec benchmarks, and then actually in this class I just introduced the spec CPU benchmark. So we use spec CPU benchmarks for measuring the performance of a CPU, but we can also measure the performance of other components such as the I/O or some server systems or also graphics. So spec also provide the other type of applications to measure the performance of other type of components. Okay. And then now to measure the CPU performance, we use the spec CPU. Actually, the most recent version of the spec CPU is the 2017 version. And then usually we use the 2006 version, but the most recent version is the 2017. And then actually the spec provides the compiled binary. Actually, the spec benchmark provides the source code of the benchmark, and then we can compile this source code with the compiler, and then we can run this compiled binaries on the testbed computer system. This testbed means that, oh, I want to measure the performance of this computer, and then this computer system is called the testbed computer system. Okay, and then I also mentioned that the spec CPU provides the many different types of application, usually, and then we can divide these application types as the integer type application and then floating point type application. So we will learn about the integer data type and then floating point data type in chapter 3. But you need to remember that so integer is simpler. Actually, the floating point is number system is more complex. So usually integer type data and then floating point type data requires the different type of processor engine. Okay, that's why the spec also split the integer type benchmarks and then floating point type benchmarks. But our CPU can run any data type, right? Because we use the both number systems like integer or floating point number systems. So our CPU supports these two types of data. Okay. So okay. No, that's the example of a spec benchmark. So This table shows the example of stack benchmarks. So actually the integer type benchmarks, and then also this table shows the result of stack benchmark. So as you can see, so if you use this column, then you can find the which application is used for as the spec speed benchmark, spec integer type benchmark. So like the GCC is the compiler, C compiler, and then you can find that our X264 is the video compression, then also the data compression application, so call interpreter. So you can find that different types of applications for in the spec integer benchmarks. So in this table, you can find the instruction count here, and then CPI is the CPI of Intel Xeon. So as we learn, you can find that, oh, if the applications for different applications exhibit different CPI, and then I also explained because actually the CPI is the average CPI is determined by instruction types. Then applications have different fractions of instructions. Okay, that's why the CPI is also changed different for different applications. And then clock frequency, actually clock cycle time is the same because it's the same hardware, Intel Xeon. And then this is the actually spec speed measure the latency, the response time of this application on this processor. And we can calculate the execution time here. So you can result here. And then the important thing is that we can find the reference time. So why do we need reference time? I said, not to measure the performance, actually we need to measure the performance of a test bed with the performance of a baseline machine, so reference machine. So we need to compare the performance of two different computer systems. So spec also provides the reference execution time using the reference computer system. This is the execution time of the reference computer system. Then how can you measure the performance? You can just compare the execution times. Okay, so PA divided by PB equal, so let us assume this is the reference machine, then it's the execution time of B divided by execution time of A. This is important, right? So you need to know. So this is the performance value. And then this performance value is called the spec ratio. Okay, so you can find this number here. And then also you can find that this number is the this execution time of the reference machine divided by execution time of the test bed machine. Right? So it's the 2.83. So using the spec applications, we can calculate the spec ratio, and then there are many applications. And then we can calculate the geometric mean for these different applications, the spec ratios of different applications. And then we can use this value. So spec ratio of the Intel Xeon is the 2.36. So which means that compared to reference machine, the performance of Intel Xeon is 2.36 times higher. Okay, so we can measure the performance like this. Okay, so benchmarks are selected popular applications which are used for measuring the performance of a computer system. Also, spec provides the spec power benchmark. And then actually, so then how can you measure the power consumption of our computer system? So actually, spec provides some different metric for the overall SSJ OPS per watt. So what does that mean? So SSJ underbar OPS means that server side Java operation per second. So actually, this is similar to the number of executed. Sorry. Number of executed instruction. Sorry about that writing. Okay. And then spec just measure the number of executed instructions per consumed power. It's very similar to the performance per power. Okay. So why do we need to focus on the performance per power? So so things like this. Our mobile computer system, like our smartphone. Our smartphone will consume very low power. Okay, but problem is that also the performance of our smartphone CPU is also very, very low. So mobile CPUs or embedded CPUs consume very low power, and then also the performance is low. So, but let's think about the server CPU. The performance of the server CPU is very high, but the server CPU also consumes very much power. So in order to compare the power consumption fairly, then we need to also focus on the performance per power. So it's actually it is the performance per running cost. So it is related to the performance that we can get by the cost we invest. Okay. And then also the spec calculate this metric like using this equation. So as you can see, the power consumption is accumulated for I equals 0 to 10, and then also the SSD OPS is accumulated for I equals 0 to 10. What does that mean? Actually, the spec just measure the power consumption for amount of workload. Okay, I believe you can understand if you see this example. So this is the target load. Target load means the amount of workload that can be executed by server computer system. So that is the capacity of the server computer system, right? So actually full load means that 100% means that is the full load. So which means the number of instructions or the amount of workload is equal to the amount of tasks which can be the maximum amount of tasks which can be executed by the computer system. It's the full load. Okay. So actually the target load is the 100%. So every CPU resources are used, then this is the performance. Actually the performance is proportional to the target load. And then you can also measure the power consumption of this server system. And then by changing the target load percentage, like 90, 80 to 0%, then we can measure the also power consumption of the server system. And then this is the overall sum of the SSA OPS, right? Here. And then also we can accumulate the average powers for target load percentage. And then we can calculate the spec power metric like this. Then why spec power? Why does spec power measure the power metric like this? What's the problem? That's right. But the more important issue is that just focus on this line. So I mentioned that we want to get calculate performance for power, but it means that if we use this metric, then we assume that if we invest more cost, which means that if computer system consume more power, then performance can be increased. Right. So just to see this metric, the performance per power consumption. So which means that which means if we invest more cost, the cost is high, the performance can be high, but it's not proportional. What does that mean? A server computer does not need the target load is 0%, but its computer system consumes this much of power, the 48 watts, 10%, 115. So actually, the performance of power is not proportional. So this is the performance, and this is the power. Sorry. This is the load amount of task, and this is the power. We assume the target load is increased and power is also increased, but it's not true. Actually, in the real computer system, this is not proportional. So it is increased like this or like this. That is the power proportional problem in our computer system. So for example, if the 100% of load is our server computer system will consume 347 watts, but if the 10% of load, our computer system will consume 115 watts. So it's not proportional, even though the amount of workload is reduced to 10%, but the power consumption is reduced to the 33%, 1/3. What's the problem? If the target load, if our server system run 10% of workload of the maximum load, then the power is wasted because this workload is not proportional to the power. So actually, if we run the 100% of load, so if we use the 100% of the total performance, we can run the server computer system more efficiently. Okay. Actually, it is very critical for the data center because the data center has many server computer systems. But for the personal computer, it's not critical, but it's very critical. Okay, because of its money. Okay. So I also explained how we measure the power consumption with the step benchmarks. Okay, So let's talk about the Moore's law. So Moore's law is the very popular law in the computer industry, and then actually it's very important. Then, what is Moore's law? The performance or number of transistors. Actually, the Moore's law means just focus on the number of transistors, not performance. Real, double, or triple? Double, right? Every 2 years. So actually, Moore's law is not theoretical law, it's the empirical law. So what does that mean? Actually, the Moore is the name of the Intel CEO, the co-founder. So which means that actually it's Gordon Moore. Gordon Moore observed the trend of semiconductor technology, and then he found that the number of transistors, the number of transistors per one CPU chip, a single CPU, is exponentially increased by year. That's what was law Moore, Gordon Moore observed the semiconductor industry. So it is because the transistor size is reduced by advanced transistor technology. Then why Moore's law is important? Actually, it is based on the observation, but CPU vendors make target code based on the Moore's law, and then also they expect the advances in semiconductor technology based on Moore's law. Think like this. So everyone wants to buy their CPUs because they need to also invest money to buy CPU. But if the CPU performance is not changing, so it's not improved, then no one will buy new CPU, right? So for example, so I bought my laptop in 2018, but now so currently it's 2022, and then if the performance is the same, then I will not replace my laptop computer, right? Because performance is there. So, but because of the advances in semiconductor technology, so which means that the transistor size is reduced to actually the CMOS transistor. CMOS transistor size is reduced, and then in the same area, we can add more hardware resources in the same area, same chip area, which means that the performance can be improved. So if the CPU performance is improved, then I want to buy new computer. So that's so based on the Moore's law, the CPU vendors such as Intel may have made plans to build a new CPU generation. Okay, that's why Moore's law is actually important. So actually, the Intel removed this statement on their homepage, but actually maybe 5 years ago, then Intel showed that their statement like we tweaked the Moore's law on their homepage, which means that we can make better CPU year by year. Okay. But recently they removed this statement because it's very difficult. It's very difficult to make the smaller transistor, right? So nowadays Intel is using 7nm technology, but actually Intel was very struggle to use the 10 nanometer or 14 nanometer technology. Actually, Intel for a long time, we used the 14 nanometer technology for their CPUs. Okay, and so they struggled to use the advanced semiconductor technology recently. So it's not so recently. It's very difficult to track Moore's law, but it is important. Okay, so I also copied the definition of Moore's law from Wikipedia, and then if you read this definition, so you can find that Moore's law is just the observation. So it's just law based on the observation, and then the rules actually for the Moore focus on the number of transistors, not performance. Okay. The performance is determined by many factors, but this number of transistors is determined by semiconductor technology level. Okay, the rules every 2 years. Okay, but Moore also modified his law based on the semiconductor technology. Okay, so let's see this graph. So you can find, this is the transistor count. The x-axis is the also year. So you can find that the y-axis is the log scale. So and then based on the Moore's law, in a single CPU includes more transistors, and then this number of transistors have increased linearly in this graph. So which means that it's exponentially. It is because number of transistors double every 2 years. So which means that it is increased exponentially. Actually, this is very amazing. The vastly advanced technology. But what's the problem? Actually, we track the Moore's law. So actually, it's somewhat old data because we are here. But if you see some trend, and then this orange triangle represents the number of transistors per CPU, and we can find that it is linearly increased. So also the y-axis is the low scales. So which means that the semiconductor industry tracks the Moore's law. Okay, number of transistors increased. So single thread performance is saturated because of our consumption, as I mentioned. Then also the frequency is saturated. So we cannot, it's very difficult to use faster computer, faster CPU. Actually, the clock frequency is saturated. So, but power is increased and then saturated. But what is changing? Number of cores are increased. So actually, the performance of a single core is saturated because of a power issue. But CPU vendors tracks the Moore's law, so which means that we can use the smaller transistors. But with the smaller transistors, what can we do? We can add more cores. Okay, so it's very hard to increase the frequency. And then, but we can use the smaller transistor like here. So which means the number of transistors per CPU chip is increased continuously. Then what can you do? It's very hard to increase the frequency. Then, we can add more cores. So if we add 4 cores, then we can increase the number of transistors by 4 times, right? So that's why we use the multi-core recently. But unfortunately, as I mentioned, the Moore's law is ending. So which means, so nowadays it's very hard to make smaller transistor. So recently the Samsung, eh, they introduced the 3 nanometer technology that I believe the TSMC is using a 5 nanometer, or so they are targeting 2 nanometer technology. It's very small, right? But the trend by Moore's law is just and recently. So which means that it's not easy. It's not easy to use better transistors on our computer CPU. The problem is that if we use the better computer, if we use smaller transistors like better semiconductor technology, then we can include more transistors in a single CPU chip. So even though the performance of this single core is saturated, then we can add more cores in a single CPU chip. So which means that we can increase the throughput easily. Oh, Moore's law is ending, so it means that it's not easy to increase the throughput. Okay, so actually the frequency is really saturated, so it's not. So actually, the performance of single thread is saturated from early 2000, and then also it's slightly increased, but it's nearly saturated recently. But using multi-core architecture, then we can increase the throughput. It is becoming more difficult. Okay, Moore's law is ending. So actually, this graph shows the Moore's law of the 1975 version, and then it's the real trend of Intel. So actually, so sometimes the Moore changes his law, but actually recently the Moore's law is ending. Okay, but traditionally, processor industry is developed based on the Moore's law, and then based on the Moore's law, we can invest more hardware resources on our CPUs, and then by investing more hardware resources, then we can increase the performance of a processor. That's why Moore's law is very important. And then because as Moore's law is ending, we also focus on some advanced architecture, such as the domain-specific architecture. So it's some advanced topic, so I will not explain about the domain-specific architecture in this course, but the computer architecture plan is changing percent. But we are learning about the basic concept of the computer architecture. So I will just mention the 8 great ideas in computer architecture field. The first is the design for Moore's law. That's why Moore's law is very important. So Moore's law just observe the trend of semiconductor technology, so which means that in 2 years we can invest more transistor in the single CPU chip. So and then based on this expectation, we can also add some techniques or ideas and some components in our CPU chip. And then let's see the other 7 ideas. Use abstraction. So I also explained about the abstraction in the first day of the class, and then actually the computer engineering field use the abstraction. Abstraction very frequently. It's very important concept. We use abstraction for simplifying our design, okay? Because the complex details are hidden, and then only the required information is provided to the operator. So that's why the software engineers do not know about the detailed architecture or detailed structure of computer hardware because the complex information is just hidden and then just required analysis such as the you can use the CPU core like this. You can use some large amount of memory for your application. That's it. Just write your code. So we just for simplify some design, then use the concept of abstraction. And then make common case fast. Why is it important? So for example, is it because the CPU runs the general purpose application, right? So that also suppose it. Our CPUs runs these operations 90%, and then some other operations 10%. Then we need to focus on this part to increase the performance. Why? So for example, if we focus on the 10% part, 10% portion of some workload, then we increase this part as so let us assume we improve the performance of this part as 10 times. It's amazing, right? Then this workload is the execution time for this workload is reduced to 1%, but in overall, the performance of a computer system is just improved less than 10%, right? So even though we increase the performance of this part 10 times, the overall performance improvement is very small. Okay, so we need to focus on common case fast. And then performance can be improved by parallelism. The parallelism means 병렬화, which means that many tasks or the multiple tasks or multiple instructions can be executed simultaneously. Okay, then the parallel. And then pipelining also is very important concept. We will learn about the pipelining architecture in chapter 4, and then prediction. Higher memory hierarchy. Actually, prediction is the advanced architectural ideas. So actually, you will learn about the prediction, advanced computer architecture course. But prediction is also very important. Memory hierarchy is the backbone of the computer system. So we will learn about the memory hierarchy in chapter 5. And then actually this is the last idea is the dependability. But it's related to the reliability. It's also advanced concept. But just remember this is 8 great ideas in computer architecture. So we add some ideas, architectural ideas. We also improve the CPUs based on these ideas. Okay. Okay, so this is the end of the chapter 1. Then so we learned about the basic concept of the computer systems. Then we also learned about how the software is compiled and how this compiled software is executed in the hardware. And then we also learn how to measure the execution time, because in order to measure the performance, we need to focus to measure the execution time. And then we need to compare the performance of our CPU with the performance of a reference CPU. Okay, then power. We also learned about the consumption of the CPU. Okay, end of the chapter 1. And then I know I do not share the chapter 2 slide because I found that I need to modify some contents in the chapter 2. Sorry about that. But I briefly introduce about the chapter 2. Okay. So also as you know, I posted the homework assignment number 1, and the homework assignment number 1 covers the content in chapter 1. So please start the homework question by yourself. So then so it will be very helpful for your study in computer architecture. So actually, questions include the what you learned in chapter 1. Okay. Okay. So in chapter 2, we will learn about the instruction and then instruction set architecture. So if you see some subtitle of chapter 2, then you can see that the language of the computer. So actually in chapter 1, we learned that we write a code using high-level languages, high-level programming languages. But computer systems cannot learn these high-level languages. So these high-level languages should be translated into machine languages. Okay, and then these machine codes are executed by computer hardware. So then think about this. When you learn about a language, then we learn the meaning of word, like the apple. Apple is some of the fruit, which is red and which is sweet, and then also something like sugar very small particle, so it's also very sweet. So something like that. If we learn about the word or languages, then we also learn the meaning of word, meaning of a language. So it's the same to the computer system. Computer system receives the instruction like the add x1, x2, x3, like this. Computer receive the instruction. This is kind of word. Then, what should computer system do for this instruction? We need to define the meaning of instruction. And then this meaning of instruction is defined in instruction set architecture. Okay. So actually, when this instruction is given to a CPU, then actually the definition, which means that the required behavior, the required result for this instruction is defined in instruction set architecture. And then this CPU is designed based on the definitions in instruction set architecture. So CPU generates the result. I will explain here. So in chapter 2, we will learn about the instruction set architecture. So you can see the very funny figure here. So you can find that this is hardware and this is the software. So and then also between the software and hardware, you can find that instruction set. So instruction set means that it's the bundle of instructions. So which means that actually many instructions. Okay. So what does that mean? Instruction set is the interface between software and hardware. Actually, I also mentioned the abstractions in computer systems, but the software engineers write the code using high-level languages. And then when they write a code using high-level languages, and then they actually they do not consider about how the works for their application. They just write the code. Okay. So they are running on here, and then also between the hardware and software, there is an instruction set. Actually, the software engineers do not know about the instruction. So because the high-level language code is translated into the instructions. Okay. And then, the hardware is here. So hardware using these instruction sets, hardware execute the applications. Okay, but in order to run applications, then the hardware need to work very hard. So which means that actually the hardware generates the result based on the instructions. Okay, so they are working here, and then hardware is working under the instruction set, and then software engineers work above the instruction set. Okay, the instruction set is the interface between software and hardware. Okay, so let's see the concept of the instruction set architecture. So this is this very simple figure. Okay, then what is a processor? A process, then what is the meaning of a processor in a computer system? I want to explain. So what is a processor? So I also, as you can see, I drew a figure like this. Actually, the definition, right? The main role of the processor is that a processor receives instructions here, and then processor generates the result from instruction, and then this result includes the change of states. So what does that mean? So something like this: add x1, x2, x3. So you will learn about the meaning of this instruction. So, but like a equal p plus c. So using a calculator, then we can execute some arithmetic instruction like this: a equal p plus c. Then what are required? Actually, we all know the meaning of this instruction. So this is that we just perform the p plus c, and then the result is stored in a, right? So actually, like a calculator, instructions of a computer system handle data, actually number data. Okay, it's very similar to a calculator. So as you can see, this is an example of an instruction. Oops. So you can easily understand, oh, this is the add instruction. Actually, this is the plus add instruction. And then there are three columns. So actually, this means the x1 equal x2 plus x3. So okay, this instruction is very similar to this calculator instruction. And then as you can see, it performs x2 plus x3. So you can take it and do it those number data. Okay. Change of state means that the data in computer systems are changing. So state means the actually data. Okay, so when the instruction is given to processor, and processor changes the states in the computer system, so which means that a processor changes the data in computer systems. So that is the main role of a processor, computer system. Then, actually, we will learn about the different types of instruction in chapter 2. Actually, the instructions have many different types. Then these instructions are given. Then, actually, when the instructions are executed, data in these components, like register files or main memory, are change. Okay, so we will learn about the register file or main memory in chapter 2. But just to remember this figure, it's very simple. Instruction is given to a processor, and then processor generated a promised result. And the generating a promised result means that the data stored in register file or main memory are changing. Okay, so this is the concept of a processor, and then this figure shows how instructions are executed. Okay, so and then I will briefly explain about the basic concept of instruction set and the instruction set architecture. So in next class, I will also introduce about the RISC-V instruction set architecture, and then also basic some basic instructions in RISC-V. Okay. Okay. So I will stop here. Then any questions? Okay. Thank you for attention. Then see you in the next class. 네, 감사합니다.